Okay, apologies guys, I have to re-record this because my recording didn't work, so we're going to do the standalone video lecture for lecture 12. So a couple quick announcements. I have my office hours this coming Monday, normal time. Apologies for the illness last week. We have an extra office hours done by the TAs this coming Tuesday. As a reminder again, midterm 1 is coming up. Make sure your CFA bookings are in place. Also, Canvas Quiz 2 is now open. Opens on Saturday afternoon. Remember, it is due by 5 p.m. on February 6th. And as a final reminder too, if you want to participate, we're asking you to please create questions to put on Piazza. Remember, these are midterm style questions where you are asking to draft the question and come up with an answer to post to allow students to practice. This is a really good chance for you to practice, and like I've mentioned, we will use one of these questions in the actual upcoming midterm as well. So in last class, we introduced you guys to the final routes to carboxylic acids. This is where we're generating carboxylic acids by nucleophilic capture of CO2, and the retro reaction, the decarboxylation. This is where we convert a carboxylic acid back into some precursor. Remember, you have to have that beta carbonyl for that to work. We also talked about the haloform reaction, and finally the Strecker synthesis. This is a reaction which is actually 3 individual steps, so amine formation, nucleophilic attack to an iminium, and then hydrolysis of the cyanide or the nitrile group. So there are different configurations of reactions we've already discussed in class. Okay, for today's review question, we're asked to predict the products of the following reaction. So take a second, review this, look at the 2 starting materials, and think of what reaction you might be expecting. So if you look at the functional groups, we have a carboxylic acid, we have an amine, and if your first thought is, well, not much is going to happen here, there's not quote-unquote a reaction, that might be correct, but remember, there's still sigma bonds that can be broken or formed. The process can still happen. It may not be what we would consider, maybe a very dramatic reaction. In fact, the major thing that's going to happen here is a very simple acid-base reaction. The amine is our more basic center. The carboxylic acid is quite acidic, so we expect us to be able to form. The major thing that's going to happen if you mix these 2 things together is just a proton transfer from the amine, from the carboxylic acid to the amine. So we make the protonated conjugate acid and the conjugate base of the 2 materials we form. That's the most likely way to complete the system. And again, it's just back to the relative reactivity and the properties. Another way to ask this question is, well, why wouldn't you? Think about this as, I'm a primary amine that kind of looks like a carbonyl. Forget this for a second, right? This is a carbonyl at the center of a carboxylic acid. Why wouldn't we say something like an imine formation might be possible? And being clear, this is definitely not what we form. And there's a couple reasons for that. This is not a simple carbonyl. It's not like an aldehyde. It's not a ketone. The carboxylic acid is not nearly as electrophilic as either of those 2, because remember, resonance is going to be donating electron density into that carbonyl center. It's not nearly as electrophilic as an aldehyde or a ketone is. Second thing too is we've got this acid function. Proton transfers are very rapid. It's very easy to do these acid-base reactions, and if you have a possibility of doing an acid-base reaction or something that looks more like a dehydration in this case, you're going to get primarily the acid-base reaction happening preferentially. More importantly, once we've done this acid-base reaction, these are your 2 species. This molecule is no longer, it's not a nucleophile anymore. We've tied up that lone pair, so there's no nucleophile, no nucleophilic character in this component. Same thing, this one is not an electrophile. We've added this negative charge here. That negative charge is spread out over these centers. The relative that what we would normally need is sort of a delta positive center here. That's not present because we have this formal negative charge spread out over that point. So the 2 structures we have, these are very stable, and they're no longer going to react with each other, so it's not possible to do anything like this. In fact, if we really wanted this reaction to work, to do something where we're maybe making a carbon-nitrogen bond, we need a whole other series of reactions, and that's what we're going to discuss today. This is carboxylic acid reactivity, where we're reformatting the carboxylic acid into different structures. And today we're going to talk about esters. To make our esters, we're going to do this by alkylation, diazomethane reactions, and Fischer esterification, and then finish off by introducing acid chlorides. So today's players, these are our components. Now if you notice, they're all at this high oxidation state. So here we have two carbon-oxygen bonds and another carbon-oxygen bond here. They're at one level of oxidation higher than the aldehydes or the ketones. And it's similar for things like esters, the alkyl halides, or specifically the acid chlorides. All of them have this kind of three individual heteroatoms attaching to that carbon center, and that's high oxidation state. So what we can do is a series of reactions where we can interconvert between these different structures. We're going to talk about that sort of transformations. Note here that esters are different than carboxylic acids because that proton there has now been replaced with this carbon center. What we call acid halides have either a fluoride, chloride, or bromine attached to that center, where the most common acid halide or acyl halide that we deal with are these acid chlorides. These are the ones that we're going to be using as our main workhorse for certain transformations. So as a quick introduction to esters, you guys are probably familiar with esters as a class of molecules. They're the odorous molecules, or something that produces smells of a lot of fruits. So you may have made these in the lab. This is where you condense together two molecules to create something that smells like banana or smells like orange. Every one of these molecules has this common ester center. That's this carbonyl to carbon-oxygen bond where you have some carbon fragment attaching to it. And the nature of the smell is coupled to the structure. So here you see banana is this bridged isopropyl kind of unit here in the end. This linear chain gives it the citrus smell, or this more complicated structure here has this more strawberry kind of smell associated. One of the other interesting things too, these are all volatile molecules, so when they form, it's a signal, a biological signal for us of a ripeness. When we smell these kind of good smells, this is an indication the fruit is ready to eat. Now, if you've left out these kind of fruits, one thing that can happen is they rot, and you can actually have the unpleasant smells, which is actually from decomposition. If you look at this, the ester group here can be hydrolyzed about these kinds of bonds, and what that does is it produces small molecule alcohols and carboxylic acids. Those hydrolysis products are usually sour smelling, and they're the ones that we associate with something that is spoiled. So you can kind of think of these molecules in the biological context as triggers for indication of things like both ripeness and food spoilage once they get hydrolyzed. So the esters are the indication of the fresh or ready to eat, and their hydrolysis products, where we're breaking them down, is the indication of decomposition. So overall, in general, esters can be formed think of them strategically as one of two major routes. So we're either starting from our carboxylic acid and we're replacing just this hydrogen where this oxygen remains in place. So I'm just tracking to say that that oxygen is the same oxygen we've had here. We're deprotonating, removing that hydrogen to create our carboxylate. That carboxylate is going to act as our nucleophile, and we're adding an alkylating agent, something like an alkyl iodide or a powerful electrophile, and we're adding that to this oxygen center. The most important thing with this route is we're replacing this hydrogen, and the new bond we form is right here. The original carbon-oxygen bond here stays in place the whole way through. That's not the same for a reaction under acidic conditions. When we're under acidic conditions, we're actually replacing this whole OH group. So what happens is we're going to do a protonation. We're going to add a proton to the system under acidic conditions. That activates our group, and that makes it possible to bring in a nucleophile. So in this case, this is our nucleophilic component. This means this is our electrophile. And again, as an opposite, the carboxylate is our nucleophile in the first case. That makes this our electrophilic component. So we've reversed the polarity of the two fragments we're bringing together. When we do that, we're effectively breaking this bond right here to kick out water, where the new fragment coming in is bringing in both the oxygen and the R group. So once again, that's the bond that we're forming over here, where in the first case, we are forming this OR bond. It's the one external to this point. So this is just a strategic way to look at the two fragments you're going to be needing and also map out the type of starting materials needed for the particular reactions. Alkylation and diazomethane reactions, those follow this basic profile, and Fischer esterifications, those are acidic. These follow the acidic pathway here at the bottom. So first, let's start with the easy ones. If we're going to do esterification by alkylation, as we mentioned, we're going to do an addition where we're replacing this proton with some type of a carbon group. Now, to do this, we're going to need in general, carboxylates are not too bad nucleophiles once we can form them, but we need powerful electrophiles. Methyl iodide is really what we're really gunning for here because we're going to be doing an addition via an SN2 type pathway. Now, if you notice these conditions, typically what we're going to have is the addition of something like triethylamine. That is a small amine where we are tertiary, so we have 3 ethyl groups. So it's kind of sterically bulky. We're using the lone pair to pick off this proton and form our carboxylate nucleophile. Now, why that's important is in the second step, we're bringing in methyl iodide. That is our SN2 electrophile here. So we want a base, in this case like triethylamine, because it is only acting as a base. It is just a nitrogen with our lone pair. We're going to protonate it to make this triethyl ammonium conjugate acid. Now, the reason we want a simple base like this, if we use something else like, let's say, hydroxide. Hydroxide can act as a base, but it's also, because it's anionic, it's a pretty powerful nucleophile, and it'll actually start to compete with this addition. So this is why for these kind of alkylations, we're going to use relatively weak bases, usually these tertiary amine bases, in order to selectively form the carboxylate, and that becomes my SN2 nucleophile to get my desired product. Now, one of the things of note of this, typically alkyl iodides are the only molecules that we can use in these cases. It really does require very good electrophiles, so we're pretty limited about the type of carbon structures we can add. So here is just the overall mechanism drawn out. Once again, let's add the arrows. We're going to do an acid-base reaction in this first step to make our carboxylate. Second step, we're using that nucleophilic character to add an SN2 reaction, displacing iodide, which is our good leaving group, and most importantly also the methyl center is a relatively unencumbered carbon center, so nucleophilic attack is actually quite favorable here for an SN2. So just showing that part out here, these are the two steps that we would have under these conditions where we're going to do an acid-base reaction for deprotonation and then finally an SN2 to bring them together. So, quick review question. If you looked at these 3 molecules, these are all alkyl iodides, if we had to rank them from fastest to slowest, which one do you think fits into what category? So take a moment, maybe pause the video, think about it, and come up with your answer. So in this case, we can probably separate these out into these 2 here are both primary. They're at a primary center in these cases, so we expect these 2 to be faster, and then this one, this is a secondary center. So we're going to assign this one as definitely the slowest. Now, if you look at these 2, you might be tempted to say, oh, well, this has got 3 carbons, this has only got 2, maybe this is less sterically bulky. In fact, the fastest one is this guy right here, what we call an allyl iodide. That's spelled A-L-L-Y-L, and that's referring to this 3-carbon fragment with this pi bond right here. That's what we're referring to as allyl. That's that carbon structure. Versus the ethyl iodide is going to have a sort of a second or number 2 ranking in terms of their speed. Why this one is faster is kind of 2 parts. Remember, this center over here, these are sp2 centers. They are flat, and because of that, they actually take up less space sterically than, let's say, the methyl groups that are presenting at this point. Remember, to do this reaction, we actually need to have, let me just redraw this here. This is our number 1. The nucleophilic substitution we're going to do here is going to have our nucleophile, and it will attack in an SN2, that's 180 degrees to our leaving group, attacking the center. The allyl group, the transition state that we're dealing with in this case, is going to look something like this, right? Where we've got the iodide leaving, and and the nucleophile coming in at 180 degrees, right? That's an enforced geometry. Because of that, because we have this sort of geometry here, this center at the transition state builds up this delta positive kind of center. That is not a formal carbocation, but having this kind of electrophilic buildup here, the adjacent pi bond actually can sort of help with a delocalization, help stabilize this buildup of a pi bond too. So you both have an electronic situation that's helping with this ejection of this iodide, and we have a steric congestion. This pi bond, because it's flat, actually has a little bit less of a steric encumbrance than something like the methyl group. It's small, but still, because of those two factors, the allyl group is actually going to be slightly faster than my ethyl. Now, in terms of the esterification, we can check here. We can use an allyl iodide to make something like allyl esters. So if I took a carboxylate, it's possible to take allyl iodide as our electrophile in place of the methyl iodide. So that's possible. If we wanted to make something like this one I would say is generally not what I would choose. Even adding this one methyl group here compared to something like methyl iodide is okay. The ethyl iodide really is going to take me a long time. It's not my first choice for two reasons. This is a very slow reaction. Even the addition of this one methyl group here really does slow it down to be productive. It's not very productive. And there's just better ways to add this ethyl group. You'll see this when we get to Fischer esterification. What I really want to emphasize is when we go here, there is no way we are going to do esterification on a secondary center. Just by going to the secondary centers, the carboxylate nucleophile is no longer effective to do this. The temperature and the time that would be necessary to make this happen is really not feasible. So if we have to do substitutions, if I wanted to make the ester with this kind of carbon fragment, I would not be using alkylation. So the thing I'm really trying to emphasize here is when we're talking about the alkylation mechanism, you're pretty much limited to something like methyl iodide, allyl iodide, okay. Going over to something like even ethyl iodide, that's probably a really bad choice. So while alkylation is a relatively simple reaction, you're really, really restricted for the kind of carbon groups you can add. So the next one I want to bring up is this diazomethane esterification. Now it's related, similar conceptually, to the electrophilic, nucleophilic alkylation like we talked before. So it's the alkylation kind of category. We're actually going to be doing a reaction where we're removing that proton, and then this carbon center is the one that's being added over here. So it still has that same sort of mechanistic similarity to the alkylation using something like methyl iodide. Now what's different about this is we're using this new reagent we're introducing called diazomethane. So it's a new functional group that we're introducing now. Quick trivia fact, diazomethane is a very explosive and toxic gas. It's relatively dangerous to work with. We do have ways of sort of generating it in situ, so we can start with this compound called trimethylsilyl diazomethane. Again, don't have to worry about it, this is just for facts, but the point is, diazomethane is a really interesting mechanism and a very effective way of adding a methyl group to these carboxylic acids. We actually use these for things like alkylating or adding a methyl group to every carboxylic acid in very complex mixtures. Typically, we add this to things like biological mixtures where we might have a whole bunch of different carboxylic acids in the solution, and I want to 100% guarantee that every one of them is going to be turned to the methyl center. Now, just as a quick introduction, diazomethane is a molecule where if we draw it out here, that's the formula. The Lewis structure of it would look like this. That's one way to draw it out based on the bonds we have. Now, if you notice, the formal charge of this nitrogen here would be positive. What that has to give you is a negative charge out on this nitrogen over there. Now, that's one of two different resonance isomers. The other way to draw this is I can actually promote this negative charge over in that sort of sequence where I'm actually parking a formal negative charge on this carbon, and then I'm actually bonding it like this. Now, there's kind of two things I want to emphasize here that is actually similar to what we've discussed with things like the enolate isomer, resonance isomers we've talked about before. So down here, these are the two resonance isomers that we would typically see of enolates. Remember, in this case, this is probably the more stable form because it puts the electronegative oxygen, gets the negative charge, but that means this is a more reactive center. So the enolates, we typically use them as carbon nucleophiles because of the increased nucleophilicity or reactivity of this center, but we typically draw them as these kind of oxygen-centered anions. In a similar way, nitrogen here being more electronegative, this is probably the more stable resonance isomer, but then this is also the more reactive resonance isomer. So in fact, they act pretty much like carbon anions, at least at the very beginning. So this may be the larger contributor, this is the larger reactivity, and it guides the reactivity by saying it's going to act like a carbanion when we do the reaction. So that's actually really important for how this mechanism works. Again, strategically, I like to use diazomethane when I want a methyl group to be added to a carboxylic acid, and I don't want to have to add anything else to the system. I don't want to have to add another base. I don't want to have any chances that a methyl group is not being added to my carboxylic acid. And the reason why I don't need a base comes down to, again, that resonance structure. So let's draw it out like we did here. So I'm emphasizing that negative carbon structure, and I'm going to have my positive nitrogen. Oh, excuse me, positive nitrogen is on the center carbon, like this. It's our hypervalent center. So when I'm drawn like this, I take this negative center, I'm going to grab this proton, I'm going to do an acid-base reaction first. So that's the consequence of this diazomethane. It's actually basic, and because it's a very small center, right? This is just a CH2 minus. There's really no steric crowding there. It can act very easily as a base to give me my CH3 plus, H3 to N triple N positive charge here. Now, if you look at the situation you've had, what happens is if I add diazomethane to a system, it's going to diffuse around until it finds an acidic proton. When it does, we can do a relatively quick acid-base reaction. We transfer the proton over to this methyl center, and we make our carboxylate. Now, the carboxylate is my nucleophile, so this is now a nucleophilic material, making this a really, really powerful electrophile. And if you just look at this in terms of the bonding order, there should be a couple things that jump out at you. So here we have methyl, so that's similar to, think of this kind of equivalent as like methyl iodide, right? It has that same kind of disposition, but there's actually something really special here. If you look at this, that's not just a good leaving group, that's like nitrogen gas that's barely hanging on to this carbon here. So while iodide is a pretty good leaving group, this here, we would be eliminating N2 gas, which is probably the single best leaving group on the planet. So it's this innate piece here where we have this basic character first in our diazomethane, which allows us to do this deprotonation that both generates my nucleophile and generates my super powerful electrophile, and they're in close proximity to each other. After this proton transfer, this is now perfectly lined up to do an SN2 reaction, which then gives me my methyl ester. So this is kind of an interesting trick. This is why we use diazomethane, because it's this acid-base reaction that acts like the trigger to make almost this explosive electrophile to rapidly functionalize here. And so this is why we can do methylation with absolute certainty that they really only get added to these acidic centers after that proton transfer has happened. It also explains why diazomethane is so dangerous, because as soon as you add a proton from any sort of acidic center, you make a molecule that's ready to liberate nitrogen. That's a very common component of most explosives, is these kind of energetic reactions that liberate gases like nitrogen. So this is just drawn out in more detail. This is the two-step process. First, our acid-base reaction to produce both our good nucleophile and our good electrophile pair, and then an SN2 kind of reaction to give us our methyl transfer and nitrogen gas. And again, this is a really powerful reaction. Again, slightly limited, right? Because diazomethane is a relatively hard molecule to deal with. If you did want to make another molecule where we change that sort of payload, it is possible to make something where we have, let's say, a larger R group and diazo. So molecules like this do exist. They're just called other diazo molecules. So we could have ethyl, diazoethane, or diazo whatever. Just the downside is that they are relatively hazardous to handle, and they need some special conditions in order to form. So it is possible to use this general strategy to expand to other ones. It's just practically, and for the purpose of this course, we're really only going to consider methylation using something like diazomethane. Okay, so now we move to the second mechanism. This is Fischer esterification. You may have seen this before, and this is actually probably one that you've run in the lab at some point. Here we take a carboxylic acid, the alcohol, and our catalytic acid. And as we mentioned at the beginning, the difference here is this is our nucleophile in this case. Because of the acid catalyst, this is acting as our electrophile, and this OR fragment here corresponds to that part here. So we're breaking and forming this bond here, we're ejecting here, and this OH is what's actually being lost as water in that case. We'll go through the mechanism in more detail in the next chapter. So if you talk about this, so this is looking similar to, at least in terms of energetics, we're starting with a molecule at that sort of number 3 oxidation state, and we have that same kind of oxidation here. In order to get this reaction to go to completion, typically we're going to have a lot of extra alcohol. These are catalytic acid, and we will work under dehydrating conditions. So this follows the same pattern that we've seen before using Le Chatelier to drive these reactions to completion. So in general, we shift the reactions and the equilibrium using a large excess of the alcohol component to it in order to make our products. In general too, the reason to do this is because we use high boiling alcohol, something where we can actually help to remove the water from the system. As another just a data point, you may have ever heard of something like biodiesel. Now remember, biodiesel, if you've seen them, what we have is triglycerides. These are fats, like vegetable oils and things like that. What we have is glycerol and these long chain fatty acids. So these carboxylic acid fatty chains, this is what actually makes up things like cell walls. This glycerol, or this triol, is our backbone. And then in order to make biodiesel, we would take something like methanol, and we're converting it, where we're clipping this bond here to make these new methyl esters. I only mention that in case you've seen it before, but it's a similar kind of concept. We take a large amount of these alcohols, in this case the solvent would be methanol, and a catalytic acid in order to convert them over to products. So the thing for right now is just to recognize where these molecules come from. Under Fischer esterification, what we're doing is we're taking a carboxylic acid and a nucleophilic alcohol in order to form the fragment that we're trying to target. So in this case, if we're trying to make this banana alcohol, we would be using this as our alcohol starting material, and the carboxylic acid is this fragment over here. So remember, we're clipping the bond here. So the two starting materials we would need would be acetic acid and this simple alcohol like that. Those are the two fragments we'd have to put together to make this particular artificial scent. Now for our practice try it later, same sort of question. If imagine you're going to do Fischer esterification, look at these two esters, how would you form them? So take a second, maybe pause the video. All right, so the first one here, again, each time we take the ester. If we're using Fischer esterification, we cut this bond here. So we'd separate that into this carboxylic acid, which would be our electrophile, and in this case, ethanol is our nucleophile. In the latter example, that's the bond we're cutting here. That gives us this aromatic, this benzene ring, like this, as the carboxylic acid, NH2, and methanol as our nucleophile in that case. Now, one more thing to talk through here is how we might get an intramolecular esterification. So remember, intramolecular means that we are doing a reaction inside the same molecule. In this case, this is our nucleophilic center here, making this our electrophile. So we would be doing a Fischer esterification where both the nucleophile and electrophile are part of the same molecule. So here, let's say this is our center number 1. We're going to be attacking the center and breaking this bond eventually. So that's carbon 1. It's going to attach to the center here, 2, 3, 4, 5, and 6. So if we were to do an intramolecular reaction where we're forming this ring to form this ester, we would make a 6-membered ring like this, and again numbering it off, that's 1, 2, 3, 4, 5, and 6 to give you that sort of visibility. Once again, that's the bond that we're forming when we do this, and we are making 1 molecule of water every time it closes like that. Now for the second one, if you imagine we had to go and this is a callback to our first year, 121. If you remember, you're going to do, let's say, a polymerization reaction, something where you were going to So if we were going to do an intramolecular reaction, this is where we're reacting all the pieces together to make this cyclic molecule. If you remember, polymerization, this is an intermolecular reaction where we're reacting between these different fragments. This would be like taking this guy here and using the nucleophile from one of them with the electrophilic center from a second molecule. So if we were going to make a polymer, you can start off by saying, let's say I'm going to leave this alcohol attached, that's one end of the polymer. I'm going to make an ether at the other center, so here, and then we have the same sort of carbon chain over to that center, and then we have the terminal part, one of the other last alcohols. Here it would terminate as, let's say, the carboxylic acid, where in this case the repeating unit is this chunk right here. We'd have N of those here. This is a polyester. And again, this is something we see in things like clothing and things like that. Once again, these are just two different possibilities. If you had really high concentration of this molecule and high temperature, you tend to form the intermolecular reaction. At very, very high dilution, where it's hard for one of these molecules to find another one of them, then the intramolecular reaction to make these cyclic structures would typically be preferred. Now for our last topic, we're going to talk about acid chlorides or acyl halides. What these are is a group of molecules where we've replaced a halogen at this oxygen center. So we've replaced the OH from the carboxylic acid with something like a chloride, fluoride, bromide, or iodide. Now just for reference, our most common ones are these acid chlorides. They sit right in that sweet spot of being reactive enough for us to form, but not so reactive that they are very difficult to handle. It turns out that most acyl iodides are just really too unstable, so practically we don't use them at all. Acyl bromides are possible, but again, really crazy reactive. And really what we're saying there is this comes down to the efficiency of these leaving groups. Iodides and bromides are too powerful of a leaving group. Chlorides are sort of perfect. Fluorides are okay, so you can kind of imagine as the Goldilocks point where the chloride is right in the middle in terms of reactivity and stability, so making them the kind of the workhorse of these acyl halide reactions. So we'll talk primarily about these as we move forward. Now you can think about them as they're like carboxylic acids, they're derived from carboxylic acids, but we've replaced that acidic OH with a good leaving group, which allows us to do some very useful reactions. That means that most nucleophiles, almost any nucleophile, can react with these, so they become a very reliable way of adding an acyl group to other centers. So the thing we're just going to talk about today is how we form them. Now, you use a series of reagents. We've listed a bunch here. Now, we just want to show you some general properties, and this should come back to something similar to what you've seen before. If you remember, I can take something like a primary alcohol, and I can use a reagent like what you see here, this kind of sulfur in the center with a chloride, I can use that kind of a reagent to turn this, at least initially, into something like an O-tozol, right? Eliminating maybe chloride as my nucleophile. And if I continue to heat it, I can actually push that all the way through to the chloride center. This is a reaction you guys may have seen in 203 or 233, but the similarity I'm trying to draw is the reactions you guys are used to now is you would start with some type of reagent, in this case something like a sulfonyl chloride. That's going to contain both the chloride component to it and some sulfur or phosphorus group that originally reacts with this oxygen to make this activated oxygen species. We've removed this hydrogen, and then we're coming in with this nucleophilic chloride to displace that whole group, and that's the strategy we use to do this kind of 1-2 punch. First, activate the oxygen, come in with nucleophile, replace it with the halogen. If you look through the series, we have that same kind of pattern. All these reagents are things where you've got this kind of sulfur center and a packaged halide. And what that does is it replaces this oxygen with our halogen, and the oxygen fragment, this oxygen here, ends up departing with the sulfur. We can use something like PBr3, where here that's our bromide, is our packaged halogen, and the oxygen departs with the phosphorus. Or something like this POR3, so like POCl3, where once again you're bringing in the halogen here, that's what gets incorporated, and the oxygen from the center departs with the phosphorus. So it's similar to what we've seen before for things like conversion of alcohols into halogens.